Hello everyone, my name is Mayur Thoke. Today we are going to see Revise Yourself video on implementation of queue using link organization. Implementing queue using linked list. A queue is an ordered collection of items where the addition of new items happens at one end called the rear and the removal of existing item occurs at the other end commonly called the front. The first element to be inserted is the first one to be deleted, hence it is called first in first out FIFO and last in last out LILO list. Real life example of queue are people standing in queue to buying tickets and walking in queue. Why we want to implement queue using linked list? The major problem with the queue implemented using array is it will work for only fixed number of data value. That means the amount of data must be specified in the beginning itself. Queue using array is not suitable when we do not know the size of data which we are going to use. A queue data structure can be implemented using linked list data structure. The queue which is implemented using linked list can work for unlimited number values. That means queue using linked list can work for variable size of data. No need to fix the size at beginning of the implementation. The queue implemented using linked list can organize as many data values as we want. We will implement queue using linked list. Queues maintain two data pointers, front and rear. Front to know first inserted element, rear to know last inserted element. Queue is very simple data structure. You only have to manipulate front and rear to get queue property. Basic operations. Following are the basic operations of queue. Main queue operation ENQ. Insert an element at the rear of the queue. DEQ. Remove the and return the front element of the queue. Auxiliary queue operation. Front. Display the data front of the queue. Queue size. Return the number of elements stored in the queue. Display. Display elements of queue. There are many different operations that we can implement. For example, merging of two queue, sorting of queue. Let's see implementation of queue and its operation. With example for linked list, we will make structure of a node using struct keyword in which we here talking int data and one pointer of the that structure to point another node. First we will take two pointers of that struct node, front null and rear null. ENQ. Inserting an element in queue. Initially both of our pointers pointing to the front and rear are null. Now if we enter the 12 in queue, we will checking whether there is any implement present or not. If rear is null, we make our front and rear pointers to find our newly inserted node having data 12. Now again, if we want to enter new data, let's say 45, we will check for rear null or not. Now our rear would be pointing to 12, so 45 will added next to the rear node and 45 will be our rear node. Same way, if I add 26, it will be added after 45 and rear will point to the node having data 26. ENQ value. Inserting an element to the queue. Steps. We can use following steps to insert a new node into the queue. Step 1. Create a new node with the given value and set new node next to null. Step 2. Check whether queue is empty. Rear equal to null. Step 3. If it is empty, then set value equal to new node and rear equal to new node. Step 4. If it is not empty, then set rear next equal to new node and rear equal to new node. DQ. Deleting an element from queue. Now by doing 3 enq operations we will be having queue having 3 elements as shown in the figure. First we check that front is a null. If it is, then queue is empty. We cannot perform dequeue operation. Then but here front will be pointing to 12. So if we want to delete element from queue, as our queue is FIFO, first in first out, 12 is first inserted, so 12 will be removed. Our front pointer will be pointing to the 12. To remove it, first we make our front pointer to point the element inserted after 12, and then simply we free the memory. As simple as that. 45 and 26 will be removed. If we perform two more dequeue operations, and again our queue will be empty. Rear and front will be equal to null. Dequeue operations. Deleting an element from queue. We can using following steps to delete a node from the queue. Step 1. Check whether queue is empty. Front equal to null. Step 2. If it is empty, then display queue is empty. Deleting is not possible, and terminate from the function. Step 3. If it is not empty, then define a node pointer temp and set it to front. Step 4. Then set front equal to front to next and delete temp free temp display. To display all elements present in queue, we will take one temp. You can give whether name you want pointer and make that to point front. Then we transfer up to rear, or we can say temp equal to null. Using temp equal to null, next which we will make our pointer to make towards rear and print temp one data. Display the element of queue. We can use the following step to display the element nodes of queue. Step 1. Check whether queue is empty. Front equal to null. Step 2. If it is empty, then display queue is empty and terminate the function. Step 3. If it is not empty, then define a node pointer temp and initialize with front. Display the temp data and move it to the next node. Repeat the same until temp reaches to rear in bracket temp next null. Finally display temp data to null. Complexity. Time complexity of a DQ and NQ operation is O1 because there is no loop in those operations. Time complexity of display operation is O(n) since we are transversing to print each n number of elements. Space complexity is O(n) where n is a number of elements. This is the example of implementation of a queue data structure using linked list in C programming. This is the output of that program. Application of queue in operating system scheduling process and threads. CPU scheduling, disk scheduling. In printer, files will be in queue to be printed. When data is transferred asynchronously, data not necessarily received at the same rate as sent between two processes. Example include I/O buffers, pipes, files, I/O, etc. That's all from my side. Thank you.